Let us see this remark. Now, what does above result says? X n goes in probability to C if and only if limit n going to infinity probability that mod of x n minus C greater than or equal to epsilon is 0 for every epsilon greater than 0, which is equivalent to saying that limit n going to infinity probability that mod of x n minus C is less than epsilon is 1 for every epsilon greater than 0. So, it says however small epsilon you take, x n would go in probability to C is equivalent to saying that the distance between x n and C can be made arbitrarily small with probability 1. So, this in fact suggests that if x n is going in probability to C, it suggests that in certain stochastic sense, as n is becoming large, x n is taking values only near C. So, above result suggests that if x n goes in probability to C as n goes to infinity, then x n is stochastically very close to C for large values of n. Such an interpretation does not hold for the concept of convergence in distribution. That means, especially when you have a convergence to a non-degenerate random variable. Then what does the convergence in distribution suggest is the distribution of x n is converging to distribution of x. That does not mean that x n is going close to x. So, especially if x n goes in distribution to x as n goes to infinity, where x is some non-degenerate random variable, then it cannot be inferred that x n is getting too close as n goes to infinity in any sense. All we know in that case is for large values of n, the distribution of x n is getting close to that of x. Now, let us give another easy to verify condition for convergence in probability. So, let x n be a sequence of random variables with mean as mu n's and variances as sigma n squares. Suppose that mean converges to mu and variance converges to 0, then x n would converge in probability to mu, and that is what our intuition would also suggest, because mean is going to mu, variance is going to 0, that means heterogeneity is just vanishing. So, that means the random variable is going very close to mu, and that is what the inference is. The result is very the proof is straightforward using Chebyshev's inequality. So, fix epsilon greater than 0, then probability mod of x n minus mu greater than or equal to epsilon, these being probabilities always greater than or equal to 0, this would always be less than or equal to expected value of x n minus mu whole square by epsilon square by Markov inequality or Chebyshev's inequality. Let us try to see what is expected value of x n minus mu whole square. So, I add and subtract mu n. So, this is what it becomes. So, this becomes expected value of x n minus mu n whole square plus mu n minus mu whole square plus 2 times mu n minus mu, they are constant. So, expected value of x n minus mu n, but expected value of x n minus mu n is 0. So, this quantity would be 0. So, the cross product term here would be 0. Now, this same as sigma n square, this is a variance plus mu n minus mu whole square. Now, this quantity you can see is clearly going to sigma n square is going to 0, mu n is going to 0, mu. So, this would go to 0. So, that means as n goes to infinity, this quantity is going to 0. So, by a result which we did, this would say that x n goes in probability to mu. So, then this is what happens, this is going to 0. So, this implies that limit n going to infinity probability mod of x n minus mu greater than or equal to epsilon is 0 for every epsilon greater than 0. But by a result which we just did, this is equivalent to saying that x n goes in probability to mu as n goes to infinity. Now, in the next part of this module, I will state a useful result which will be useful in proving some additional results. So, now let us consider the next result, which essentially says that convergence in distribution is equivalent to convergence in the corresponding moment generating functions. So, let x n be a sequence of random variables with mg of m n's, and suppose x is another random variable with mg of m, and suppose there exists an h greater than 0 such that m n and m are finite on minus h to h. So, that means the moment generating function m n as well as m, they are finite on some neighborhood of 0, and suppose there is a convergence of moment generating function of x n to the moment generating function of x. So, limit n going to infinity m n t is same as m t for every t belonging to minus h to h. If that happens, then x n goes in distribution to x. So, this result turns out to be very handy in situations where movement generating functions are easy to handle. So, if you have to show the convergence in distribution, try to show the convergence in corresponding movement generating functions, provided movement generating functions exist in a neighborhood of 0. Now, before I prove the main results, let us do this mathematical lemma. So, let C n be a sequence of real numbers such that C n goes to C. Then limit n going to infinity 1 plus C n by n to power n goes to e to power c. Now, when C is a constant, then you must have done in your plus 2 that limit n going to infinity. This result is very well known from your plus 2 mathematics. But what is being said over here is, even if C depends on n, as long as C n is going to C, this quantity would still be in limit e to power c. The proof is very simple. What you do is you consider left hand side suppose as T n. Now, consider log of T n, which is n times log of 1 plus C n by n. Now, let us consider f x, which is log of 1 plus x. Try to expand this in Taylor series. So, it would be same as f 0 plus x times f prime xi x. Xi x is between 0 and x. So, that is why this quantity would be nothing but f 0 you can see is 0, because log of 1 plus 0 is 0. So, this would be nothing but n times 0 plus x, x is C n by n. F prime is 1 upon 1 plus x. So, 1 upon 1 plus xi n. Xi n is between 0 and C n by n. Now, note that as n goes to infinity, C n by n goes to 0. So, that means xi n by Sandwich theorem would go to 0. So, that means log of T n, that is y, would go to, so this goes to 0, and this n gets cancelled. So, this would go to c. So, log of T n goes to c. So, that means T n would go to e to power c, and that is what this result says. Now, let us try to consider the Poisson approximation to binomial distribution. Now, this is I have given as one of the exercises also, but it can be proved using the last result. So, suppose x n is binomial n theta n, where theta n is between 0 to 1, and suppose limit n theta n goes to theta. Then x n would go in distribution to x, where x is same as Poisson theta, the Poisson distribution with mean theta. So, what it suggests is, if you have a binomial distribution where number of trials are large, that means n is going to infinity, and probability of success theta n is very small, so that n times theta is a fixed quantity, then binomial probabilities can be approximated by Poisson probabilities. So, very useful result which says that if you have a large number of trials and probability of success in each trial is small, so that n theta is a fixed quantity, then I can approximate binomial probabilities by Poisson probabilities, and Poisson probabilities are easy to calculate. This we do by movement generating function. We know the movement generating function of x, which is Poisson theta, is nothing but e to power theta e to power t minus 1, so which is empty. The mgf of x n, which is binomial np, which is same as 1 minus theta n plus theta n e to power t by n. So, I write down this as 1 plus n theta n e to power t minus 1 by n to power n. Let us call this as this whole quantity as C n. Now, C n is going to n theta n is going to theta e to power t minus 1. So, this is what is I have written down like this, and I know that C n t is going to theta e to power t minus 1. So, this whole quantity would go to e to power theta e to power t minus 1, which is nothing but mgf of x. So, this is what is happening. So, limit n going to infinity m n t is e to power theta e to power t minus 1. Now, this is mgf of f x, which is Poisson theta. So, that means x n goes in distribution to x. So, this result tells you that in certain situations binomial probabilities can be approximated by Poisson probability.